Hey guys, I wanted to introduce our last topic that we're going to talk about in freshman science. Generally, we have a little bit more time to cover it, but I think it's a really important topic to understand moving forward into your next classes. Um, so, this last unit is about chemical reactions, and chemical reactions are obviously a really big part of chemistry. Um, this is where one chemical changes into another one, so it's a huge portion of what we study in chemistry. Um, so I wanted to address a couple things in the lesson today. What is a chemical reaction and how you can tell a chemical reaction is happening, and what's going on with energy in chemical reactions. So a chemical reaction has to change one substance into a new substance. And people kind of get this confused with a physical change. So a chemical reaction or a chemical change has to turn one kind of matter into a different kind of matter. So it can't be, mixing does not constitute a chemical change. Okay, if I mix salt and water, I still just have salt and water mixed together. There's still salt still has a lot of the same properties the water does, and I can separate them out relatively easily. If I take a piece of glass and I break it, that's not a chemical change either, because I would just, although the glass would still be glass. Okay, so those are all physical changes, is what I'm describing. A physical change, the matter has um, the same properties, so hardness, density, those kinds of things, color. So burning sugar, turning sugar into a black substance, giving off smoke and heat and things like that, that would be a chemical change. But dissolving sugar in water or melting sugar or melting ice, those are physical changes. Like water is still H2O, whether it's solid or liquid or gas. Okay, so it's just at different temperatures, but it's still the same substance. Um, so, um, Generally, when a chemical reaction happens, when one kind of matter turns into a new kind of matter in a chemical change, it's accompanied by some evidence. So there's usually like six or seven things that you can see. Not obviously not all of them at once, but maybe a couple of them that you can spot. So how can you tell if a chemical reaction is occurring? Big one is if gas is released. If there's bubbling or fizzing, um, not from boiling, but just bubbling or fizzing, that would be an example of a chemical change because gas is produced like baking soda and vinegar, those kinds of things. Color change is a really obvious one. If I was to burn sugar, it would turn from white to black. If you ever roast a marshmallow, it turns kind of brown. That's a chemical change that's happening there. Um, Formation of a precipitate is one that we don't see quite as often outside of the chemical lab, but that's when you have two liquids that mix together and a solid sort of drops out of it. That's something you talk about a lot more in your chemistry class your junior year. Change in temperatures. This could be something that's getting hotter or colder by itself. Maybe you mix some things together and they get hot or cold or something. Light released. Sometimes this is a flame, or it could be a glow stick or something. Um, just gets red hot when it reacts. New odor given off. This one is more of a something that you'll see in organic chemistry. Sometimes you're reacting things together and you can't tell that anything happened other than there's a strange smell being given off that's different from any smell before. And sometimes you can't see a reaction, but you can hear it. You'll do one like this called the barking dog when you're in a chemistry class. One I would have liked to do with you where you react two invisible gases together and all you can do is hear it. Um, so let me go through some examples to kind of get you to think about what's physical and what's chemical. So here I've got an apple. If you ever cut an apple or an avocado or a banana, if you just kind of let it sit out for a while, eventually it changes colors by itself. It turns from this sort of nice light color to a real dark brown color. That's an example of a chemical change. Okay, so because the substance, this part of the apple is different. It's a different chemical now. It tastes different. It's softer. It has different properties. Leaving metal out, it changes certain iron type metals. They tend to rust. And so rusting is a different color. It has different hardness and density, so it's a different material. So rust is different from regular metal. So that's a chemical change. It's a new kind of substance being formed. Boiling water. This is one that confuses a lot of students because you think, well, it's giving off a gas and I'm heating it up. Isn't that a chemical change? Well, if I ask students what's inside these bubbles, I always tend to get weird answers. When you heat water up, you start to see these bubbles. What's in a bubble? What gas is in there? Is it oxygen? Is it just air? Is it hydrogen? The answer is inside these bubbles, it's just water vapor. Okay, so this is water and this is water. It's all just water. This is a physical change when you boil water. Painting over rust, you're changing the color, but the rust is still underneath. So that's just a physical change. Two others that tend to confuse students. Burning a candle. This is giving off light and heat by itself, so it has to be a chemical change. Then my students come back with, well, isn't it just melting the wax? Isn't the candle just all going to melt? If you ever burn a candle before, you know that it goes away. The wax burns up into carbon dioxide, just like burning a log or something like that. So the wax and the wick and all those things, that's changing into a new substance. So burning a candle is a chemical change. It's got a smell, it's giving off heat, so that's a chemical change. Sand, when sand gets wet, it changes color. So you think, oh, that's got to be a chemical change, right? It's a new substance, but it's just wet sand, even though, so this is just a mixture. Okay, so mixing a light paint with a dark paint isn't a chemical change because it makes a new color. It's just physical. So mixing is just a physical change. Okay. So I wanted to talk about why do chemical reactions actually happen. And the key idea I want you guys to get is that all chemicals want to become more stable. And so on a molecular level, I don't know what this drawing is supposed to be. On a molecular level, there are some things that are just more stable than others, certain ways that atoms and molecules want to be arranged. So this is a picture from a place called Garden of the Gods in Colorado, where there's all these rocks that seem like they're just about to tip over. And a lot of chemicals, sort of on a molecular sense, are just like that. They're just about to tip over and roll downhill. And that they're unstable in the sense that something could activate them to give off all their energy. A rock like this has a lot of potential energy. Chemicals also can store potential energy that can be given off, okay, when they can get to a more stable place. Okay, so there's a couple kinds of reactions I want you to be familiar with. And not like anything specific that I want you to know is reacting, but using this idea of energy, I want us to think about a couple things. If you ever notice with roller coasters, we've talked about this in the energy unit, roller coasters, most of them start the same way, that you get sort of propelled up a hill, and then once you reach the top, this is the Raptor, you just roll through the rest of the ride. Okay, the Millennium Force the same way. Most roller coasters are the same way. What you're being given at the beginning of the ride is actually potential energy. Okay, so in order to get the ride started, you have to put a little bit of energy in, and then you get all that energy back out as kinetic energy for the rest of the ride. Chemical reactions are the same way. You have to usually put energy in to get them started, but once they meet a certain energy limit, we call it activation energy, the reaction will continue by itself, just like a rock rolling down the hill. So you have to push the rock just a little bit, but after that, it's going to roll all by itself. Okay, so all chemicals contain a certain amount of chemical energy, which is basically potential energy. And so during a chemical reaction, you have to put a little bit of energy in, and then the rest of the reaction happens by itself. Okay? There's two different ways that this can happen. In one case, you can be given off only a little bit of energy. Imagine if you had a reaction that just only gave off a little bit of energy after you put a lot of energy into it. Or maybe you have a reaction that you put some energy in and then it rolls even farther downhill and you get even more energy out. Well, these are two kinds of reactions that we call exothermic and endothermic reactions. Okay, so depending on how much activation energy you put in and how much activation and how much energy you get out, the reaction could overall be giving you energy or it could be taking in energy. Okay, so there's two different kinds of reactions. The exothermic reaction overall gives off more energy than you put in. So these reactions tend to feel hot. And this turns out that because of the nature of chemistry, these reactions are much more common. If you think about it, most chemical reactions that you could do around the home, like burning things or, burning is a really common example, or there's lots of baking soda and vinegar gets hot, those kinds of things. Those give off energy in general. Another reaction, well, actually, baking soda and vinegar might not get hot. I need to try that one. There aren't very many reactions that get cold. When you mix two things together or you let something sit, it gets cold by itself, at least not on a scale that you notice. Photosynthesis, plants making sugar from sunlight, that's an endothermic reaction because it's taking in energy from the sun and building sugar molecules. So that's taking in more energy than it's giving off. But there are a lot of times endothermic reactions tend to feel cold. So those take in more energy than they give off. Let me show you an example of each one of these. Glycerin is like an oil. It comes from fats and oils. So you're seeing some light given off, some gas being given off, color change. Notice how once it's already hot, the reaction happens a lot faster because it already has the activation energy to get started. Okay, it doesn't have to wait on it because it already has that activation energy. Okay, so that would be an exothermic reaction, giving off more energy than it's taking in. Example of an endothermic reaction is one that I usually like to do in class, but I like the way this guy does it.
I brought some barium hydroxide octahydrate and some ammonium nitrate, and I'm going to combine them. There's the ammonium nitrate, and there's the barium hydroxide. And I'm going to mix these two together. Hopefully I can get it all in there without spilling it. Put the top on because it generates ammonia, which stinks, and then just kind of mix it around here. It's very endothermic. So I've got this little block of wood here with some water on it. I'm going to show you how endothermic it is by putting this. It's all mixed up. It's a nice slurry now because all that water has been released. And I'm going to stick it on that block, and I'll come back to that in a moment. Yeah, it is there. So that block it's so cold that it froze the water that I sprayed onto the block, and that's actually frozen right onto it.
So that one's endothermic, taking in energy from the surroundings, which freezes the water. Okay, so you can remember that just because the reaction is giving off energy, if it's giving off energy, it should feel hotter. Okay, the reaction feels cold, it's taking in energy. So just because it's taking in energy doesn't mean it's raising temperature. It just means that it feels cool to the touch. So that's all I wanted to say for the introduction to reactions, and I have an activity that we're going to do later on this week.